This video is on the bipolar junction transistor, and more specifically on activation. As an example, let us talk about the NPN. And the NPN, and any BJT for that matter, is just basically two diodes head-to-head or back-to-back. In the case of the NPN, P is what I would call the head, because that's the one that usually receives current in a diode. So this is the head of the junction to the right, of the PN junction to the right, and that P region is also the head of the PN junction to the left. And overall here we have NPN. Between that junction we have that high concentration of electron carriers will tend to diffuse on over to regions of lower concentration. And on the left, we also have high concentration of holes, which will tend to diffuse on over to the right. As they diffuse, they leave behind, they vacate behind a region that we'll call depletion region. And they will continue to diffuse until they build up an electric field that opposes that diffusion action. When it reaches equilibrium, we have at the end a depletion region between every PN junction. So here this is one depletion region, and here is another depletion region. Somewhere in the middle of that region is where we would call the metallurgical junction, which is where we literally have where the end device stops being N and becomes P. The distance between the metallurgical junction is what we'll call the base width, and we call this the base because this region was the physical base for the first prototype. So the other thing about this structure is that the base is very short. Now notice, because of the depletion regions, the effective base width is even shorter. And this is important in how BJTs work. So let us talk about activation and biasing. What we're going to do is we're going to forward bias one of the junctions, and then we're going to reverse bias the other junction. That's how we activate the BJT. Let us use the energy band diagram to describe that. So to forward bias one junction, we'll apply a positive voltage to the P base region with respect to the left N-type region here, so where it receives the negative terminal of that voltage. Applying that voltage essentially reduces the field barrier that electrons on the N side need to overcome in order to start diffusing to regions of lower concentration. Reducing that field barrier, then we have an exponentially increasing number of electrons diffusing over to the base. And that's a diffusion mechanism. The base is so short that those electrons diffuse through the base and reach the other end of the base. Now at the other end, now is where we apply the reverse bias to the other junction. So we're going to apply a positive voltage to the N-type region with respect to the P-type region against which the PN junction is connected. Applying a reverse bias then actually increases the field barrier. So there's no diffusion action from the electrons in the N-type region all the way to the right. However, since we're applying a high positive voltage on that N-type region, the electrons that reached the other end of the base now see a positive voltage on the other side, and basically they see a field that attracts and sweeps them across all the way to the N region on the right. And that's a drift mechanism. Let me remove the markers here so that I can drive the important point here. What we're saying is by forward biasing the left region, we induce diffusion of electron charge carriers into the base. Because the base is so short, they diffuse through the base all the way to the other end of the base. And since we have reverse bias on the other junction, they're swept across into the extreme opposite end of the device. And this action of the electrons going all the way from the left to the right is the activation action that we're seeking and that we achieve by forward biasing the left junction and reverse biasing the right junction. Now, the N-type terminal on the left is the one that is supplying all these negative charges. So we call that the emitter because it emits all these charge carriers. Now, the N-type region on the right is collecting all those charges, so we call that the collector. Now, the other thing is that we see that out of the collector, we see charge carriers are leaving the collector. And remember that current flow is in the opposite direction of electrons. So electrons leaving the collector means that there is a collector current going into the collector, and that's down here. That's the one that we're referring to by with I sub C. And here we see on the emitter side, we see that electrons are going into the emitter. Well, that means that the emitter current is coming out of the emitter. So that's this other term here. Now, when we reduce the field barrier of the left junction, we also reduce the field barrier for holes that can diffuse from the base region into the emitter region. So that's another current component, and it's a whole current component. And what we see is that it's current that is coming from the base into the emitter, and it's being supplied by an external terminal, and that's the base current. So the this base current is being fed into the device along with the collector current, and the emitter current is the one that basically drains those two currents. The emitter current is also composed of two components: the electron current, that is the one that actually reaches the collector, and then the hole current that is coming from the base. So let us quantify these currents. So first let us look at the electron current. Now, the electron current is a function of how many charge carriers we have available at the emitter. So it is proportional to the emitter doping concentration. It's also proportional to the ease with which these electrons diffuse in the base. And it's inversely proportional to the distance that they have to diffuse before they become part of the current. Now, since the base is so short, they only need to diffuse a short distance, and this is the effective base width. Now let us look at the hole current, and it's basically the same thing, but from the perspective of holes in the base. So the base is the one that supplies those holes, so it's directly proportional to the doping concentration of the base. It is also proportional to the ease with which these holes diffuse in the emitter. And it's inversely proportional to the diffusion length. The longer they diffuse, the longer it takes for those charge carriers to become part of the current. So overall, the ratio of these two currents, and remember, we prefer electron current because the electron current is the one that goes from end to end, from the emitter into the base and all the way to the collector. So to design a device that basically favors that current, what we can do, and let me remove markers here, what we can do is dope the emitter much higher than the base, let's say 10 times. And then we can make the base width maybe 1/10 of the average diffusion length of holes in the emitter. And if we do that, then that means that this is a ratio of 100 to 1. So that's a pretty good ratio, because that means we're getting most of the current is going from end to end. So here's what we have, what we call injection efficiency. Of the current that we're letting out of the emitter, how much of that current is actually reaching the collector? So the one that is reaching the collector is the electron current, And the emitter current is comprised of two components, the hole and the emitter. And from what we saw in the previous expression is a function of the doping concentrations and diffusion distances. And we know that we can make the doping concentrations 10 times in our favor and diffusion distances 10 times in our favor. So again, we can get an ejection coefficient that can be on the order of 99%. But we also have another mechanism. These electrons that reach the base on one end, they have to diffuse across the base, and there's a chance that they can recombine and we can lose some of that current, and that current will then go into the base terminal. So this is recombination current. If the base width is as long as the average diffusion length of electrons in the base, what we say here is that this is 1. We get about 50% of the current is lost to recombination. But remember, we can make this base width maybe 5 or 10 times smaller. So that means that this recombination current can be very small. So here we look at the base transport factor. Base transport factor is basically how much of the emitter current, emitter electron current we avail, how much actually reaches the collector, the other end of the base. And that's basically the electron current minus the recombination component over the electron current. So basically 1 minus the fractional loss of that current. And remember, if we make that base width a fifth or a tenth, this can be a very small fraction, so the base transport factor can be on the order of 95 to 98%. So if we look at translation, the transport factor of the device is basically the translation from emitter current all the way to collector current. So first we look at the injection efficiency, basically how much of the emitter current is electron current, and then the base transport factor, how much of the current that is availed at the one edge of the base reaches the other edge. We also have current gain, and it's basically the translation from base current to collector current. Now remember, the base current is basically the whole current going into the emitter, and the collector current is the electron current. But remember, we do have some recombination in the base, and when we lose some of the electron current to recombination, the base is the one that is getting that current. But this is mostly, well, we go back, we design this such that the base width is very short, so the recombination current is very low. And then we design it such that we favor electron current over hole current, and we get that this beta can be on the order of about 100. So that's a pretty good gain. Now we can write this forward transport factor in terms of gain, because we know that the emitter current is nothing but the base current and the collector current. So we can divide all terms by the collector current. We get like this, and that's what we get here. And this is the reciprocal of the current gain. So we multiply all terms by the current gain and we get this expression. And this makes sense, because if we can get the current to be, the gain to be about 100, 100 over 101 is pretty close to 1, which is the forward transport factor. That's how much of the emitter current can reach the collector. So the forward transport factor and the current gain are basically saying the same thing in two different ways. So let us look at the collector current then. So we know that the collector current is largely the electron current in the emitter, because we know that the base transport factor is very high. And then we have here another correction, and this is what we'll call base width modulation. And let me remove markers so that we can clarify this point. So if we look at the collector voltage and we raise that voltage, electrons at the edge of the depletion region will be pulled away from the depletion region. That means that the depletion region is going to expand. Putting a positive voltage at the collector with respect to the base is like putting a negative voltage at the base. And a negative voltage then will pull holes at the edge of the depletion region. It will pull them back. So what we get here is that the depletion region expands with a positive voltage. Expanding the depletion region decreases the effective base width, which basically favors the base transport factor and the injection efficiency. That means that more of the electrons that reach one end of the base will actually reach the other end, and we get a higher collector current. So this is the way we can account for that. When we have an increase in that voltage, we have a slight increase in collector current. And this is the base width modulation parameter, which we also call early voltage, after the gentleman named Early that described it. But now we go back to this emitter electron current, and that's basically the forward bias current across this junction. And that's a diode, so it's basically just a diode expression. So what we see here is a diode current, and that diode current is pretty much the one that is describing the electron current in the emitter. So that increases exponentially with a forward biasing voltage across the base emitter junction with respect to the thermal voltage. And here we have reverse saturation current, and that reverse saturation current, let me remove markers here, is directly proportional to the junction area. And if we see here in the graph, this is a two-dimensional graph, but if we try to make it three-dimensional, we know that this device goes into the board like this and like this, and this is not a very good drawing, but we can get more or less this sense of it. And here what we see in this, let's do it this way, in this square region here, if you can imagine that, that's the junction area between the emitter and the base. The larger that area, the higher the reverse saturation current, and as a result, the higher the collector current. So the main point here is that the collector current will be directly proportional to that base emitter junction area. Well, I hope this was useful. Thanks for watching.